GitHub, and there should be a link to the. Here, I'll get the archive paper too. Here it is.
Okay.
Yeah.
Okay, yeah, this is the Identity Trap and EEG Foundation models.
Yeah, yeah. It is so. Ziping Zheng is the co-director of the Schwartz Center for Computational. Is it computational neuroscience? I think. But he does like the center focuses on EEG, or this is Scott McCaig is the other co-director, and sorry, I don't know if you can hear that siren. um, uh, this is the lab that develops EEG Lab, which is is probably still one of the most widely used EEG processing packages. But I do think that this is something that is relevant for other modalities, right? And what yeah, so just thinking a lot about how to do, like at least at this point, this is more of like a BCI, right?
Right.
But you can do that, like with the Sophent group. The MedArc is the open science group.
Right.
They are doing that with fMRI as well, So it's an interesting it's an interesting some interesting issues that they bring up, especially about these kind of small data sets. And I thought this was particularly relevant because we've got this package is the I still, this is probably Neurotech X's most it's not our most starred project, but I would say that it's definitely the most it's the most active starred project. And it's filled with data sets that are probably relevant to this FM scope like analysis of how much are you kind of memorizing subjects and versus finding the underlying representations. And this is also super relevant because talking about how we're in a different age. Moab reminds me of a project from the kind of pre-deep learning age. It's definitely a pre-scaling age, right? Where again, this is where you could write a master's thesis or potentially even a PhD with a data set with like under 100 subjects, and be and that would be a lot of work. Right? It's
Right.
like this is not to minimize in any way, shape, or form like what a monumental effort that would be. but you would, I mean, I know this because I've like had grad students come to me to talk about this project and say, I can't believe, I wish I'd known about this project before I gotten started, because they were either the person collecting the data, and again, if you're one person collecting data, like if you're going to get 50 subjects, like that's a huge amount of work, right? um as well as like someone who's potentially writing the analysis classification pipeline, right? So you're developing some novel classification pipeline. um you would have to be the person to write the new one and write the ones to compare it to show that it's better than these things, right? And it's nice to think that everything is available as open source, but again, this was not the case. And this was one of the nice things about Moab, right? Was that like it was a set of data sets, and it was a set of, we're gonna to use the current lingo, we'll just talk about state of the art algorithms. But it was basically classical ML pipelines with a cool particular French twist, with this Riemannian geometries for classification, which is cool stuff. I mean, it's nice stuff, and um, but it's certainly a big part of a lot of deep learning methods now, especially if they're coming from the kind of like PyTorch geometry world, where they're considering manifolds and things like that. So but yeah, so grad students would come saying, um, this project could have completely changed how they did their work if they'd known about it in advance. Yeah. That said, this is even when you combine all these data sets together, it is still, um, it's a great effort, but it's not what we would call like a scaled effort. Not, certainly not in the tech sense, and not and and not even in the medical imaging sense, right? So the current FOMO 26 challenge that we're doing with MedArc is doing, for MICI, is using a data set of 300,000 MRI scans, right? So this has got a much smaller number of some of the data sets that are in here, um, uh, are very small, and so it's saying now I mean 3,500 subjects, and so I'm curious what that's going to include. One of those, I assume, is a new data set that they've added that has like 1,000 plus. Somehow this has been bumped up with like one particular edition. Um, but yeah, the this is it's an important consideration that I think we can actually bring to other like topics of medical imaging. And uh, so it's like I've already taken this FN scope analysis and I applied it to a large data set of MRI scans, where we're not looking for subject, but it's the Child Mind Institute Healthy Network data set, which is actually collected across 4 different locations. So that's another thing that you can use this to actually see, again, kind of like how much is it's kind of breaking apart what's, trying to do a kind of interpretable AI approach, um, that also kind of reminds me about like doing diagnostics and uh, other techniques in statistics. You know, like when you're looking at a general linear model and you're trying to tease apart like the interactions you have, what happens when you control for this, what happens when you control for that, and trying to bring that to the foundation model results that you get. So I think uh, more general than just EEG.
Yeah. So yeah, let's see what these papers look like. So this is the identity trap and EEG foundation models. So basically, they talk about these FMs or foundation models for EEG. They report strong accuracy on clinical resting state EEG, but high accuracy under subject disjoint cross validation remains ambiguous. It can reflect a genuine clinical marker or subject identity features that correlate with the label. That's what you were talking about with respect to like individual variation and versus like an actual effect. Um, we name this the identity trap and ask whether it can be diagnosed at the representation level before fine tuning. So this is where you're trying to remove basically artifacts of individual subjects. Um, and so that's what they're doing. So they propose FM scope, which is a frozen representation protocol packaging 5 diagnostics. We apply it to 3 pre-trained foundation models across 4 data sets, and then they find that the identity trap is universal. The dominance is this dominance is a removable linear axis. Erasing it improves label decoding where the label varies within subject. And then aperiodic 1 over F noise is one subject carrier. Removing it drops the subject probe. And then fine tuning amplifies label variance only in cells of the literature established cross subject marker. And so then the identity trap is a physically grounded instance of shortcut learning. The preferred cue is a measurable physiological component, and subject disjoint splitting alone cannot rule it out. FM scope separates gains reflecting a biological marker from those reflecting subject identity. So that's very good. Yeah, I mean, I'm glad that they kind of dug into what a foundation model is, and maybe some of the caveats of combining a lot of data and then thinking about things beyond mere correlation, and kind of getting at some of these things. Getting at maybe some of the things that can make a foundation model not so predictive. Then, oh, go ahead.
Yeah, I was just gonna say, like, this is interesting to just to give you, something EEG that we are going to be doing, which is this uh, this company that is doing, showing pictures to people and then trying to predict what picture they're seeing from just their EEG trace, right? Is doing this kind of like, we've trained on this data set, we've got this data set of say 10 or 20 subjects we've trained. Now we're going to fine tune it to the person that's now sitting in this chair.
Yeah.
I lost picture. Sorry. Um, and that's what this is going to be perfect for that, you know. Or like be, you know, the what we hopefully have is a very, we do have a demonstration example where it's like we should be able to fine tune better and more accurately, faster and more accurately, um, if we can remove this confound and I guess what you'd call, it's not pre-training,
Right.
but before fine tuning. Yeah,
Yeah. Yeah.
right. Yeah.
Pre
I, I'm
pre-confound removal or something like that.
yeah. I'm still learning my terminology. Anyway,
Yeah.
but I'll drop a link to this because I like this particular company in terms of what they are trying to do. Um, yeah.
Okay. So if we go back to the GitHub repo, yeah. So this is the GitHub repo. We basically have an initial public release, um, and yeah. So it's a diagnostic toolkit for auditing EEG foundation models. Um, and then they have 5 diagnostics. Um, they have a variance decomposition, subject access erasure, aperiodic or Hough ablation, and then layer-wise probe, and then direction consistency. So these are, the first one is the subject identity dominate the representation. The second is that dominance confined to a linearly removable axis, and does it help to remove it? Then the aperiodic ablation, which is the 1/f spectral component of the carrier of identity. So there's always this 1/f spectral component you can remove or not remove. 4 is at what depth does the label become linearly separable? And then 5 is, do subjects encode the task contrast along with a shared direction? So these are all, quite relevant to data analysis. Yeah, and then I guess you could audit your own data with this code. You can reproduce the paper that we just saw, and then you can bring your own data set or use some of their data sets here. All right, very good. So yeah, thank you, Morgan. And that's hugging. Oh, the hugging face.
Well,
So this
I'm
is
just
the
I'm just sharing the all joined. So all joined is this company that's trying to do, kind of like the EEG version of uh, MedArc, or the Mind Eye project.
yeah.
Um, so it's like if you go hit the all joined .com.
This one.
Yeah,
Okay, yeah.
just because it's got a nice like uh yeah, you can see their headsets in action.
Yeah. So
um
this is Enigma.
well, yeah, it's a different enigma. It's funny. Okay,
Yeah.
yeah, so that's the CEO um and actually one of the engineers, but I think enigma is what they're calling their foundation model. I forget. There's too many enigmas. There's like
Yeah.
the enigma that's working on like neural representations. There's yeah. Anyway, I'll let you get to let's get to the more presentations. But I do want to see what you can get from this in terms of improving um, uh, uh, the kind, this particular kind of use case of foundation models, and if it's can be a practical, this is obviously super relevant for Neurotech X, and some things that I'm trying to get started with student projects.